Hey students, welcome to lecture number 5 of multiple zeta waves and modular forms. So today we want to start with section number 2, where we talk about the algebraic setup. So here in this picture we finished now this section 1, where we give some taste of all these sections which follow afterwards. And so one part of this algebraic setup we are going to discuss today we already saw in section 1.2, where we talked about the products of two Riemann zeta waves, and we also talked about the products of these modified Q analogs small g last time. And today we want to describe these two products in arbitrary depths. But first we will focus on these multiple zeta waves, and we will introduce iterated integrals, which is an integral like this, and then we will define some space H, and we will view these zeta waves as a map from this space H to the real numbers, and on this space we will define the Stoffel and the Shaffer product, and then we'll see that this map is an algebra homomorphism with respect to these two products. So we start with section 2.1, where we talk about the multiple polylogarism and iterated integrals, and I want to start with an example of an iterated integral, which you also saw on the first page. So let's consider the integral from 0 to 1 of dt1 over t1. And inside this integral we will have another integral which now goes to t1 and dt2 over 1 minus t2. So this is an example of an iterated integral because we have an integral inside an integral here. And now, since this t2 is smaller than 1, we can use a geometric series. So we still have this integral here, t1, t1. And now we have the integral from 0 to t1. And here we have the geometric series of t2 to the power of n dt2. So now taking the integral of this thing here with respect to t2, we just get n plus 1 here in the denominator and t2 to the power n plus 1. So this equals dt1 over t1. And plugging in t1 and 0, so the 0 part vanishes, but we still have this t1. So we have the sum n from 0 to infinity of t1 to the power n plus 1 over n plus 1. Okay, and now this is just an integral in t1, and also here this t1 removes this 1 there, so we just have the integral from 0 to 1 of the sum t1 to the n over n plus 1 dt1. And again, taking the integral with respect to t1, we get another n plus 1 here, so we get an n plus 1 squared. And here the sum is still from 0 to infinity. And then, so we end up with the sum n going from 0 to infinity. Here we have n plus 1 squared. And plugging in 1 here for the t, we just get 1. And we see this is just the definition of zeta 2. So in other words, zeta 2 can be written as this iterated integral. And we will see, or one thing you will do in the homework, is if you do the same game, for example, with this iterated integral here. So now there are 5 integrals, and you have these two differential forms, dt over t and dt over 1 minus t, then you see if you start with the block of this differential form and then this somehow gives you this index 2 here, and starting with 2 of these dt over t and then with this and with this dt over 1 minus t, you get this index 3. So you can check by hand using the same calculation that this iterated integral gives you this double zeta value zeta 2, 3 here. And so now we want to introduce a multiple polylogarisms, and for this, so let's assume here in the iterated integral, instead of 1 we choose the real number z, which is now between 0 and 1. And if I have it here the whole time, then here in the last step, instead of getting a 1 here, we would have gotten the number z to the power n plus 1, and this sum here will be an example of a multiple polylogarithm. Well, in this case it's just a polylogarithm, so this will be Li2 of z, and you also see that if you send z to 1, we just get the zeta value, zeta 2 here. And this we want to define in general, so we will use a sum like this to define this multiple polylogarithm, and then we will see that they have an iterated integral expression, and then sending z to 1, we will get the iterated integral expression for multiple zeta values. So this is this definition here. So we define the multiple polylogarithm Li of some index k of z, for where this sum makes sense for a complex z in the open unit disk, and since this z is the absolute value is strictly smaller than 1, this makes sense for any index k, so this k doesn't need to be admissible. And then we define this like this here, so it's just like the definition of multiple zeta value, except that we have here in the numerator we also have z to the power m1, where m1 is here the largest of these m's. And also by convention we say that Li of the empty index is just 1. So clearly if k is admissible, meaning k1 is strictly greater than 1, then this object also makes sense for z equals 1, and then we have that Li of 1 is just the multiple zeta value, zeta k. And we will see, the goal is now to write this sum here as an iterated integral starting from 0 with an integral 0 to z, and then something like we saw before. And we saw that we have these two different differential forms we want to work with. So in our algebraic setup, which we want to introduce now, we want to do it in a more formal way. So instead of talking about differential forms, we will just talk about some letters. So we have these two differential forms, and this one will correspond to a letter x, and the other one will correspond to a letter y, and then we will consider words in these two letter x and y. So for example, the integral we saw in the first example corresponds to the word xy, and we will deal with these things in this non-commutative polynomial ring Q x, y. And this thing we want to give a name, and this is the algebraic setup we want to introduce now. So we want to introduce three spaces, h, h1, and h0. And to make it easier for me, so I cannot write this by hand, so my handwriting of this h will look something like this. So I will write this h for this German h here. And we start by defining this h. So what is this? This is exactly what I said before. So this will be the non-commutative polynomial ring in two variables, x and y. And inside this we want to consider a subspace which contains q plus, and then we take h, y. So what does this mean? So what is an element, for example, here in this space? So for example, we have, could write the w is, for example, this element here. And a monomial like this we will also call a word. So this space here, the h are somehow the rational linear combination of words in the letters x and y, and h1 are now the words which end in y, and also we allow so the empty word, which we denote by 1, and we call the empty word. So this is just a monomial without x and y. And the h1 contains the empty word and all multiples of the empty word and all words which end in y. So for example, this w is an element in y, in h1, sorry. But for example, this element here, the word with one letter x is in h, but it's not in h1. And now we want to introduce the following notation. So we want to introduce zk, and by zk, for k greater or equal to 1, we mean the monomial, so the word which has k minus 1 x at the beginning, and then end with some y. So this is x to the k minus 1 y. So in these are words ending in y, so especially this is an element in h1, but we can also see easily that actually h1 is generated by these z's, so 2 and so on, because any word ending in y can be written as some product, where by product I just mean the usual non-commutative product in this polynomial ring here, in this z case. So in particular, another notation, if we have an index k1 up to kr, we define that of this index to be that of k1, that of k2, up to that of kr. So in other words, this h1 can be seen as all linear combinations of this zk, so somehow it corresponds to linear combination of all indices. And since these multiple zeta values just make sense for admissible indices, we also want to define a subspace in h1 here, which is denoted h0, which will correspond to the admissible indices. And on the level of x and y, one can define it like this. So we also allow the empty word. And now we take all words starting with x and ending in y. And why does this correspond to admissible indices? So h0 is clearly a subspace of h1, and h1 were all linear combinations of these zk's. And if a word in h0 here, if a word starts in x, this means the first z here has at least one x here. So this means that this k is strictly greater than 1. So in other words, the picture we have is this one here, that so H is the space of all linear combination of words in x and y. Inside this space we have H1, which corresponds to the span of all these zk's for an arbitrary index k. And inside this space we have H0, which correspond to admissible indices. Okay, so now we want to view our objects, the multiple polylogarism and also the multiple zeta values later, as maps from these spaces to the space of functions, also to the space of numbers. So we want to view view Li as a map. Well, I can from H. So Li makes sense for all elements in H1. So what we will consider is we consider this Li as a map from H1 to the space of all continuous functions from 0, 1 to R by well, we consider it as a Q-linear map. So it's enough to just define this map on the generators. So H1 is generated by these zk's, And the image of Li on the set k, we just send it to Li of this index k. And we also write, by abuse of notation, a word gets sent to Li of this word that. So for example, if this W is this, so this means this is Z3 minus 1/2 Z2 Z1, then Li of this word, what we mean by this is that this is Li3 Z minus 1/2 Li21 of Z. Okay. So, and this we will also do later for multiple zeta values, but there we need to consider the space H0. But here this Li was defined for all possible indices, so not just for admissible ones. And now we want to prove a lemma for this multiple polylogarithm, which will be important for the iterated integral expression. And the lemma is the following. So the statement is now, if I have a word, a linear combination of words, so elements in H1 are linear combination of words, which all start with the same letter, which I denote by A. So A could be either X or Y. So in other words, this W can be written as A times U, where U is an arbitrary element in H1. Then we see, or then the statement is that if I take the derivative of this multiple polylogarithm with respect to Z, then this, depending on the first letter A, if all these words in this W start with A, then taking the derivative just means multiplying with 1 over that and removing the first letter. And if the first letter is Y, this corresponds to multiplying with 1 over 1 minus Z and removing the first letter. So, since this Li is a linear, we can focus on the generators in H1. So we can assume that this W is actually just given by one of these ZKs for some index K, K1 to Kr. And then we see that, well, this is now just rewriting this for this case here. So this was the definition of Lik. And if we take the derivative with respect to Z, then we will multiply here with m1. So this exponent here will get reduced by 1. And here this exponent is m1 minus 1. And now we will need to distinguish between the case that this k1 is 1, so either this gets removed here, or the case when this k1 is strictly greater than 1, then we still have some m1 here. So if k1 is greater than 1, so what does this mean? If k1 is greater than 1, then, so this is greater than 1, this means that this word W starts with an X, so we are in the case A equals X. But then we see, well, then this is just a polylogarithm. So if this W is AU, then this part here is just a polylogarithm of LIU, and we have Z to the power minus 1 here, which corresponds to this 1 over that. So, and again, this just means that we get this here, which is just 1 over that LIU, which is exactly the first statement here. And the other case, if k1 equals 1, so it means that the first letter is Y, then we don't have any m1 here anymore. And then what we need to do, so let me bring this up here. So here now we have no m1. So here we have a sum which goes now from m1 goes from m2 plus 1 up to infinity. And this is just, we can use again the geometric series, which just gives this part here. And this again is just the multiple polylogarithm of LIU. And since k1 is 1 here, u is just corresponds to the index k2 up to kr. So this proves the second statement here. Okay, and now we want to use this lemma to prove the iterated integral expression for these multiple polylogarithms. And for this, we make some notation here. So as I already said, we are interested in two differential forms, omega x and omega y. So it's omega depending on a letter, omega a. So omega of x is dt over t, and omega y is dt over 1 minus t. And then the statement is, if I have a word consisting of the letters a1 up to k, so these are either x or y, then for z between 0 and 1, this li of this word can be written by this iterated integral, where for each letter I have one integral here, and then depending on the letter, I will choose either this or this differential form. And this now follows directly from the lemma by induction on the k, so induction on k plus lemma. So recall the lemma was this statement here. So we want to show that LIW of z, so this is what we want to show, is given by the integral 0 to z, and then omega a1 of t1, and then here we have another integral going up to t1 of the rest here. But if so let's say omega is at w is a1u, so u is just a2 up to ak, then this part here, this is just by the induction hypothesis, this is just LIU of t1. But here now, so we have LIU, and this omega a1 here either has the term 1 over t or the term 1 over 1 minus t, depending on the letter. So here we exactly have one of these two cases, depending on the first word. So this is exactly the integral from 0 to that of dt t1 of li a1u, so in other words this is w t1 dt1, but this is just what we wanted to show, so this is just liw. And also you can check the case when k equals 1, so the induction, the beginning, or we could also choose, we start with the empty word and then the statement follows from the definition. Okay, so now we have this, and now we also want to, well, one application is now, since this li also makes sense for z goes to 1, we now want to consider the iterated integral expression of the multiple zeta values. So we also view zeta as a map from h0 to z by sending the generator zk to zeta k, and then again linearly extend this map to all elements of H0. And we also introduced this shorthand notation here, that this iterated integral is given by the integral of this domain here, where we have the product of these differential forms. And now the statement is that for an admissible word, meaning these AKs are in X and Y, and admissible here just means that this A1 is always X and AK is always Y, we can write the multiple zeta value as this iterated integral, where we set Z to 1 here. Okay, and this is exactly the iterated integral we had as an example here. So here we had the word xy, and this in this homework here we have the word, so zeta of xy xxy is exactly, well, it's exactly what you want to calculate here. And then you see that here this x, here this y, and here xxy is exactly what we just proved. But this you should do by hand using this calculation here. Okay. And now we want to give one nice application of this iterated integral expression, which gives us a linear combination among multiple zeta values. And this is called this duality. And before I state the general statement, I want to give you one explicit example. So the iterated integral expression of zeta 3 is this, because Z3 corresponds to xxy. So we have these two differential forms in this one. And now we want to make a change of variables in this integral as follows. Change of variables. So we will say the new variable S1 is 1 minus T3, S2 is 1 minus T2, and S3 is 1 minus T1. So therefore, if we make this change of variables here, what happens to this integral here? Well, this 1 minus T3 just goes to S1, dt3 goes to minus dts1, and here the integral will go to, so this will go to 1, and this here will be 1 minus T2, but 1 minus T2 is just S2. So this integral here will be 1 to S2 minus dts1 over S1. And similar, we see that this integral here, so d2 goes to 1 over 1 minus, S2. Here we have minus ds. Of course, this one here is ds1. And then we have the integral from 1 to 1 minus t1, which is s3. And here we have minus s3 over 1 minus s3, integral from 1 to 0. So now changing the order of integration here, so instead of 1 goes to s1, we go the other way, so we erase this minus sign here, and we can also change this order of integration here. So we will have the integral from 0 to 1, ds1 over s1, 0 to s1 of ds2 over 1 minus s2, 0 to s2, ds3 over 1 minus s3. And this is again an iterated integral, but now this here corresponds to x, this to y, and this to y. So this is z2, z1. So this is the iterated integral expression of zeta to 1. And there again we see the relation that zeta 3 equals zeta to 1, which we proved before by using this telescope sum and using the sum definition, but now we see that this follows directly from this iterated integral expression. And this change of variables we now want to define on our space H0 here. So what we want to define is a map on H0, which is usually denoted by tau, where this tau is now a map and not an element in the upper half plane, but I want to stick to the usual notation. So it's a map which we can define on the space H, and making this change of variables here, we see that the differential form here, which corresponds to y, goes to a differential form which corresponds to x. So on the level of words, we just interchange these two letters. So x goes to y and y goes to x. And changing the order of these integrals corresponds to the fact that this tau shouldn't be just a linear map, it should be an anti-automorphism. So this means, so in particular, it's an automorphism, so it's should send 1 to 1, but anti-automorphism means that if I take the product of two words, meaning just a concatenation, then this should be tau of the second word times tau of the first word. So for example, tau of Z3 is tau of x, y, and this should be tau of y, tau x, x, so tau y, tau x, and this is just x, y, y, with this, which is Z2, Z1. And so this corresponds to this here. And also noticed that if I apply tau to the subspace H0, so if I have a word starting in x and ending in y, like here, a word starting in x and ending in y, because it's an anti-automorphism, this tau y goes to the front, and this tau x will be at the end, and then changing x and y will assure that also this word will start in x and end in y. So in other words, this H0 is invariant under tau. And also this tau is an involution. So in other words, tau squared is the identity. And also this means that tau H0 is just H0. And now the statement we want to make is that here we saw an example, zeta of some word equals zeta of tau of this word. And this is exactly what is called duality. So we want to have this here. So the statement is, for any admissible word w in H0, zeta, this zeta map, which goes from H0 to the space of multi-zetas, zeta of tau w is just zeta of w. And the proof is just a change of variables like we did before. So we always we introduce new variables sj, which is 1 minus t k plus 1 minus j. And then we use the iterated integral expression using this change of variables, and then we get exactly this statement here. So one example is if we start with zk. So what is tau of zk? This is x, y. But this is just tau of y, tau of x, tau of x. So this is x, y. So this corresponds to z2, z1 multiple times. So in other words, one implication of this duality relation is that for all k greater or equal to 3, we have that the single zeta value, the Riemann zeta value of k, is just the multiple zeta value zeta 2, 1, 1, 1, 1, 1, where here this notation with the curly brackets mean that we just take n copies of this index here, so we have n copies here. So here this just means we have k minus 2 ones. And you can also check that this one here holds that if you have n copies of 2, 1, so zeta 2, 1, 2, 1, 2, 1, and so on, is just zeta 3, 3, 3, 3, 3. So both of them can be seen as a generalization of this relation zeta 3 equals zeta 2, 1. And this proof here of the duality follows easily from the iterated integral expression, but we will also see later a quite recent proof, which is due to Seki and Yamamoto, that there's a nice way to prove this relation here by just using the definition of multiple zeta values as a sum. And this is using a new concept called connected sums, which we will introduce in the next section. And this we will also use then to prove this duality for these Q analogs of Bradley and Chow. Okay. So now we want to introduce the Shaffer product. So, well, we already did this in the smallest devs case, and there we showed that if we take the product of two Riemann zeta values, zeta k1 and k2, we can write this as a sum like this, and the proof was using partial fraction decomposition. So, for example, zeta 2 times zeta 3 is given by this linear combination of double zeta values. And now we want to see why this expression here is a direct consequence of this iterated integral expression. So for this we write down the iterated integral expression of zeta 2 and zeta 3, which is given by this here. And now what we want to do is, one can check that we can use Fubini's theorem here. So in total, if we multiply these two integrals, what we will have is one integral over the domain of these two things here, of the product of these differential forms. And now what we will need to consider is all possible shuffles of these two domains, by which I mean we consider the case where this T1 is greater than S1 or smaller than S1 and greater than S2 or smaller. So we consider all these different ways of splitting up this integration, and also notice that the case when, for example, T1 equals S1, this is just one point. So taking the integral, this doesn't have any contribution because it has measure 0. So we just really need to consider all possible ways of shuffling these two things. So what I mean by this is we consider now all these integrals here. So one way is that these two t's are larger than all these s, which gives this iterated integral here. And here also the coloring means that blue corresponds always to a differential form x and red corresponds to a differential form y. So it really just matters what the color of these iterated integrals here are. So this means that this is an iterated integral for the word x, y, x, x, y. So this is zeta 2, 3. And another way of shuffling is that this T2 could be smaller than S1, so we just change these two. And this corresponds to x, x, y, x, y. So this is zeta 3, zeta 2, and so on. So this is also zeta 3, zeta 2. So in the end you get these 10 ways of shuffling these two things together, and which all corresponds to some double zeta value, and in the end you get exactly this linear combination of double zeta values, which also follows from this thing here. And if you recall my other video where I explained these two binomial coefficients in terms of shuffling a deck of blue and red cards, you see that in this case, this is exactly what we are doing. So we had here a deck of cards with one red card on the bottom and one blue card on top, and here one red card on the bottom and two on top, and we considered all of these shuffles, and in the end got exactly this formula here. And now it also becomes clear that this might work in general, but this we now want to make precise. And again, to do this, we want to define now a product on this space H1 and H0, which corresponds to this shuffling of words. So and this is called, well, the Shaffer product, and it is denoted by this symbol here. And we first define this on the whole space H, and this will be defined recursively as a Q bilinear product which satisfies that if I shuffle with an empty word, I don't do anything, and if I shuffle two words where the first one starts with the letter A1 and the second one starts with the letter A2, then I define it recursively by removing the first letter A1 and just consider the shuffle of the remaining parts, and in the end put A1 on front again, and the other way is I remove the A2 here, consider the shuffle of the rest, and then in the end put A2 at the beginning again. So A1 and A2 are either X and Y here, and this W1 and W2 are elements in H. So again, this example here, so the shuffle of Z2 and Z3 means I have the shuffle of X, Y, X, X, Y, and now by definition is I remove the X of the first word and consider the shuffle of this with the rest, plus I remove the X from the second word and consider the shuffle of this. And now, so we have this, and now we need to do it again. So now the first letter of the first letter of the first word is Y, so we need to put this in front. And now there's no word left, so we have the empty word shuffle with X, X, Y plus, and now take the first letter here, so this is X, Y, shuffle, X, Y plus X, so here we could do it again, and so on. And we see here, after doing some steps, one word we can already see here is, so the empty word shuffle with X, X, Y is just X, X, Y, so then we put Y on front, and X, so this gives X, Y, X, X, Y, plus, and then one would also need to multiply this out here, so one gets the rest. So this is exactly this Z2, Z3, and so on. And now also noticed that if I start with a word in H1, so H1 was the subspace of words ending in Y. So if these two words here end in Y, then also you see that the right hand side ends in Y, so the space H1 is closed under the shuffle product, but also the space H0, meaning if I start with both starts with X, then also here both starts with X. So in other words, so notice H0 are closed. And also one can show that this product is commutative and associative. So what we actually get is that this space H is a commutative Q algebra, and these spaces H1 and H0 are subalgebras. And we will denote these spaces by, so H shuffle, so by this we mean the space H with the shuffle product as a Q-algebra, and there we have the subalgebra H1 shuffle, and there we have the subalgebra H0 shuffle. And these are all Q-algebras. Okay, now we had this map, the polylogarithm, which was a map from H1 to the continuous function in 0, 1. And the statement will be now that this is an algebra homomorphism with respect to this product here. So the precise statement is this, meaning if I have two words in H1, then the product of two polylogarism of LIW and LIU is just a multiple polylogarism of W shuffle U. So in other words, this Li is an algebra homomorphism from H1 shuffle to C01R. And the way to prove this is by using our lemma again. And so the lemma, the statement of the lemma was this one here, that if we take a derivative with respect to z, then depending on the first letter of the word, we get something like this. So what we want to show now is that these two sides have the same derivative, and then since both sides vanish if z goes to 0, we have that that they are actually equal. So let's consider the derivative of the left-hand side. So using Leibniz rule, we just get that this is the derivative of the first one times the second plus the first one times the derivative of the second one. And here we assume that W starts with the letter A and have some rest W prime, and U start with some letter B and the rest is some U prime. So we see here that this derivative of this word here starting with A we can write out using this lemma, which is this here. So maybe that's a little bit small, but so using this lemma here, we can see that this part here can be written as Li of W prime times some Fa of z. And by Fa of z, I just mean these two things here. So Fx is 1 over z and Fy is 1 over 1 minus z. So this, we use the lemma here to get this part here. And here we use the lemma again to get this part here. And then we can use, so we prove this by induction on the lengths of words. And now here we have the product of two LIs where the sum of these lengths of these two words are smaller than the original one. So we can use that this is already true, so that this product can be written as a Li of the shuffle. And then we use lemma again by saying that if I have some polylogarithm times 1 over z or 1 over 1 minus z, we can append a letter here. So in the end we get that this equals this one here. And this is just, by this recursive definition of the shuffle product, is just exactly given by Li W shuffle U. So the derivatives are the same. So they are the same up to some constant, but this constant vanishes because both sides here vanish as z goes to 0. And now one consequence of this is that also the zeta map is an algebra homomorphism, because we can here, if these two words are admissible and we know H0 is closed under the shuffle product, we also get that the product of two multiple zeta waves of some elements in H0 is given by the shuffle product of these two elements. So in particular, our space Z is closed under multiplication, because if we multiply two of them, we can write this as a linear combination. So this Z is a Q-algebra, and this zeta map can be seen as a Q-algebra homomorphism from H0 with the shuffle product to the space of multiple zeta values. Okay, and so this is all we want to say about the shuffle product. And now we want to talk about the second product, which we introduced first in the first section, namely the Shaffer product, which came from the fact that we can multiply these sums and then reorder the summation, split it up into different parts. So let me recall here what we meant by Shaffer product. So in the easiest case, if I multiply two Riemann zeta values, this just meant I can split up the summation like this. So I get again a linear combination of multiple zeta values. But this idea also works if I multiply, for example, this zeta in depth 1 with this double zeta value, then I will have all these possible ways of shuffling these m's, and then I have the cases where this m coming from this sum equals some of these m's here, which give these parts here. And this we now want to describe on our space H1. So this is the definition. So the Shaffer product, which will be denoted by this star here on H1, is again defined recursively by saying taking the Shaffer product with an empty word is just the word. And then recall H1 was spanned by these, so this can be seen as a space of words in these Z1s, Z2s, and so on. So any element in W can be written as some word starting in some Zi and some Zj, and then we define the Shaffer product recursively by either putting the Zi on front and then take the Shaffer product of the rest, or the Zj in front, taking the Shaffer product of the rest. And then we take this term here, where we now put them together in one place, like here, and we add these I and j and consider Zij times the Shaffer product of the rest. And clearly this corresponds to what we have here on top. So if I multiply Zk1 Shaffer Zk2, then by definition this is Zk1 of empty word Shaffer Zk2 K2 plus Zk2 Zk1 Shaffer empty word plus, and now I have Zk1 plus Zk2 of empty word Shaffer empty word, and this is just Zk1 Zk2 plus Zk2 Zk1 plus Zk1 plus K2. And clearly the statement we want to prove now is that this map zeta is an algebra homomorphism from this space H1, where I forgot to mention. So again, this H1 Shaffer, which is now the space H1 equipped with the Shaffer product. So this is a Q algebra. So one can check again that this product here is actually associative and commutative. And this also has a subalgebra H0 with the Shaffer product, because here clearly if I have an element in H1, this means that the first Z is not Z1, but then you also see here that in the sum here, if these are not Z1, then also these are not Z1. And clearly we now want to show that this zeta map is an algebra homomorphism from H0 with the Shaffer product to the space of multiple zeta values. But similar to the case of the Shaffer product, we will first show it for another object, which will be an algebra homomorphism from H1 Shaffer to the real numbers, and then specialize to the case of multiple zeta values. And for this, we define the following object. So this is so there are different ways to call this thing. So for an integer m, I want to define these truncated multiple zeta values like this. So I will write zeta mk. So k is an arbitrary index. So it could also be k1 can be 1. And for a fixed m, we now take the definition of multiple zeta waves, but restricted the summation here by this capital M. And this is a finite sum for a fixed m, and therefore this will give a rational number. And it also makes sense for any, so here is important, it's any index, because we don't have any problems with the convergence of this sum here. And the statement we want to show now is that this satisfies the following. So for all m's and all words in H1, where we again view this as a map from H1 to the rational numbers here, satisfies that the product of two of them equals the zeta m of the stuffle of these two words. So if you go back here, you see that if I would replace these zetas here by zeta m, then this argument here wouldn't really change anything. So this formula here is also true for these truncated multiple zeta waves, which are often also called multiple harmonic sums, but here I will just call them truncated because here we truncate this summation here. And now we want to show that this satisfies this Shaffer product. In other words, if we consider this Zm as a map from H1 to the rationals, we get an algebra homomorphism. Okay, and the idea is, well, this is actually one of the homework to show this, and this can be done by induction on M. And here the reason why we introduce this M is somehow that you can do induction like we did for the polylogarithm, where we had this Z, which somehow was a connector in this induction step. And similar here, we have this M, and that's why you can prove this here by induction on M. And then taking M goes to an infinity, we see that we also get this statement for multiple zeta values, because clearly the limit m goes to infinity of zeta m of an admissible index is just zeta k. So we get the statement that the product of two multiple zeta values for some admissible words in H1 is just given by zeta of the stuffle of these two words. So in other words, we get an algebra homomorphism from H0 to Z. Okay, so now I want to summarize what we did. So we had these H0, and on this base we defined two products, the Shaffer product and the Shaffer product. And for both of these products, we had this zeta map to the space of multiple zeta values. And for both of them, this was an algebra homomorphism. And these spaces were contained in the algebra H1 stuffle. And this was contained in the algebra H1 shuffle. And on H1 shuffle, we also we had this polylogarithm, which was a map to the continuous function in 0, 1. And here we had the zeta m map for all m's to the rational numbers. And somehow here, where this is not really a map, but here, if we send m to infinity, of course it doesn't make sense for a rational number, but if we take the m goes to infinity of the zeta 1, we end up here at the multi-zeta value, and if we send z to 1 of the polylogarithm, in the case when we start in H0, we also get back these multiple zeta values. And what we will see later is that that we will be interested in comparing these two two ways. M goes to infinity and Z goes to 1. And also we will see in the next section that there are actually maps from algebra homomorphism from H1 Staffel, which will be called the Staffel regularized multiple zeta waves. And there will also be a map from H1 Shuffle, the Shuffle regularized multiple zeta values. And then comparing somehow these two limits will also lead to a direct connection which compares these two regularizations, and this will lead us to the so-called extended double shuffle relations. And now what I want to talk about is, so this will be the extended, but already in this picture here we have some double shuffle relations, namely because this zeta is the algebra homomorphism with respect to the shuffle and staffel in H0. We can also start with two words here, multiply them and take this map, and we will get linear relations, which are called finite double shuffle relations, and this picture here will later generalize this idea here. So now let's go to finite double shuffle relations. So this is just now a consequence of what we did before. If I have two words in H0, then if I take the shuffle product of them minus the staffel product, which is now again an element in H0, then applying this map zeta to this gives 0. And so this gives a linear relation, but this relation, for example, zeta 3 equals zeta 2 1, which we now already proved in two different ways, this is not contained in this, because the first relation I can get is in weight 4, because the smallest admissible words start in weight 2, namely the element Z2. So the smallest possible way is to consider the following relation. Namely, so here if I take Z2, shuffle Z2 minus Z2 staffel Z2, I will get this relation here, which gives the relation that 4 times zeta 3 1 equals zeta 4. And here's a table of these. If you count these relations, then you see the finite double shuffle relations. The first relation is in weight 4, which gives this relation here. But as this example here shows, we expect more relations. So in this row here, we have the number of all conjectured relations. So this one here is this. And also in weight 4, we expect to have 3 relations, and here we just have 1. And for example, one relation we also proved by using this duality was this one, zeta 2 1 1. So this, for example, is also not a consequence of these finite double shuffle relations. And also there's a third one, which does not follow from this finite double shuffle relations here. But this one here is an example of a finite double shuffle relations, and this relation actually has a nice generalization, which is given by this proposition here. Namely, the statement is that for all n greater equal to 1, I have 4 to the n zeta 3 1 3 1 n times equals zeta 4 4 4 4 4. And to prove this, you can show that on the level of H0, that if you take the shuffle product and this linear combination of these shuffle products of these Z2, Z2 and so on, you will get the left-hand side after applying the zeta map. And if you take the same expression, but except for the shuffle, you take the staffel product, you get the right-hand side. And then applying the zeta map, you get this one here. And since all these words are in H0, this is an example of a consequence of the finite double shuffle relations. And also, so this is an exercise, and also what is part of the exercise is to show that we have this formula here for zeta 2 to 2 to 2. So for example, if n equals 1, zeta 2 is just pi squared over 6. So this is an example of this. And if you would apply the zeta map on this part here and use this formula, what you can also show then that you get an explicit formula for zeta 44444 by using the zeta map here and this formula here, but also a nice formula for zeta 3131 and so on. And this is a so-called 3-1 formula for multiple zeta waves, which can also be proven by, or which was the original proof, by using these multiple polylogaritms and show that they satisfy. So if you consider the multiple polylogarism of this index here, you can show that this satisfies a certain differential equation. And then you also can see that the generating series of these numbers, which involves some hypergeometric series, hypergeometric functions, also satisfies the same differential equation. Okay, and now in the end, I want to introduce you some toy which you can use to calculate these shuffle and stuffle products. So for this. So if you go on my homepage, you can see, so this is the page of the course. And here under materials, you can see the quasi-shuffle products playground. And if you click there, you get the following. And here you can calculate the stuffle product. So for example, if you want to calculate the stuffle product of the index 2 and the index 3, you get that this is 2, 3, 3, 2 plus 5. And also you can use multiple lines here. For example, the shuffle product is given by this, and therefore the stuffle so the shuffle minus the stuffle gives this relation here. So zeta 2 times zeta of 3, 2 plus 6 times zeta of 4, 1 minus zeta of 5 should be 0. So this is an example of a finite double shuffle relation. And also here you can use the shorthand command that this is double shuffle of 3, so this gives exactly the same. But what you can also do is, so this is again this double shuffle of 2 and 3, and so maybe let's go to weight 6. So this is the double shuffle relation if you take the Z3 and Z3, but in weight 6 you could also choose, for example, this one here, and but what this also allows is to, for example, multiply with some number here, and let's do, for example, what is double shuffle. So for example here, one could also add this to the 6 times the last one to get rid of this 4, 2. So you can play around and get different relations. So all these relations here are now examples of finite double shuffle relations. So if you replace these indices by a zeta of 4, 1 and zeta 2, 3, 1 and so on, you see that all these give you linear relations. So this is yeah, you can play around with this, but also what I implemented here, which we will see in the next time when we talk about quasi-shuffle products, I also implemented the product of these Q-series G, which are called G-stuffle. So we saw earlier that the stuffle product of these Q-series G is basically the usual stuffle product, but you get also lower weight. And this we also had an example that in this case here, G2 times G3 is G23 plus G32 plus G5 minus 1, 12 G3. And again, you can always choose an arbitrary linear combination of these relations and these products. And yes, so please use this tool if you want to do some examples by yourself of these products. And next time we will generalize this idea of the Stafford product to quasi-Shaffer products, and then also in particular talk about this product for this function g's. See you next time.